All right, so welcome one, welcome all. This is our first attempt at this. We'll also have to see how the board situation turns out. Let's see, so last time we had gotten as far as rederiving something that you probably saw in Physics 130, to be completely honest with you. Yay? This is our Bernoulli's equation. So let's today try and get as far as this idea of an ideal gas law, and maybe even this idea of what we mean by an absolute temperature scale. So I think that would make me happy if we could make it at least that far. So let's start with this idea of molecular mass. So as this is science classroom, you can tell from our periodic table, right there. Those of you watching on video, I'm sorry, I can't turn the camera that way, but it's a science classroom, trust me. We have a periodic table on the wall. So
it's there.
Yeah.
You cannot see why it's there.
Periodic table, we have atomic numbers, right? Most of the, exactly. And I'm clearly walking off camera too. I don't know where the camera is. This is going to be a nightmare.
We know we can hear you, as long as we can hear you on the video, right? I mean, it's not like we could see you before anyways.
Tell them Google it.
Okay, so this one starts here and ends here. Okay, I got this. I really don't. So most of our atomic mass is in the nucleus, yeah? Mm-hmm. So the nucleus has some defined number of protons and neutrons for so for a given isotope, we have a defined number of protons and neutrons. We're all okay up to that point? Mm-hmm. Yeah. So all protons have the same mass as other protons. And similarly, all neutrons have equivalent mass to other neutrons. You're okay with me using the symbol P+ for protons and 0 for neutrons? The mass of a proton and the mass of a neutron are very similar, the neutron being ever so slightly more massive than the neutron. So these are very nearly equal. So our atoms approximately whole number multiples of the mass of the simple hydrogen um, single proton. And this is going to lead us to something called an AMU, an atomic mass unit. So we're going to define this as as 1/12 the mass of a carbon 12. So with that as our working starting point, the mass of hydrogen is approximately just a touch over 1 AMU. So
That's Mu or MH?
H for hydrogen. And then we're going to say that 1 gram is an Avogadro's number of AMU.
What's the subscript for the middle one?
H2O, I apologize. So far, so good. Okay. So,
What's mu again?
atomic mass unit.
Oh, okay.
So we're just gonna define this to be 1/12 of the mass of a carbon 12. 6 protons, 6 neutrons. So far, so good? Then, let's see how this works. Yeah. So, as a simple starter example for us, if we have 12 AMU,
Is that carbon?
that would be a one example of this is carbon 12. Would be 12 grams per mole, which is 12 grams per 6.022 times 10 to the 23 atoms. And that winds up being roughly 1.992 times 10 to the minus 23 grams per atom. Give or take. Yay?
That's how much an atom of carbon weighs? Is that what you're saying?
Yes. Yeah, so if I wanted to convert from an atom that has a mass of 12 AMU into a mass in grams per atom instead of AMU per atom, I just follow through kind of that simple procedure.
So the better
So
one,
if it was something else, swap out the 12 for, like if you want oxygen, put a 16 here.
okay. So the better one line on the, is that a conversion factor? 1 gram equals
Avogadro's number of
whatever,
amine, yeah.
Oh, okay.
Yeah, those two statements are equivalent. So, yeah, enough? Okay, so then,
What's the name of this 6.00022 or?
Avogadro's number, so 6.022 or 6.023, I think your book uses 6.022. I'm trying to be consistent,
Okay,
so.
I can't remember the name.
Granted, I'm old, but the number I learned was 6.023 times 10 to the 23.
I heard some comment.
This and this matched, which is how I always remembered it.
I remember it because avocado's number.
But you can remember the values?
Yeah,
Oh,
I can remember.
I mean, I'm in OChem too, so. It's-
The way that I remembered that
In
was
my
that
blood.
those matched, but apparently I was wrong, so
oh.
maybe my memory's faulty. Okay, so
Well, then if it's a non-exam, we usually give it to.
I'll give you the value to use. So I would argue that temperature is one of the most common, most familiar measurements in your day-to-day life. So I was the cliched child who no one came to his 5th birthday party. My mom ultimately, my brothers didn't even go. They got in trouble, and that at least made me feel better. But
Present gift.
I loved it when my brothers got in trouble. But my mother ultimately called my babysitter, and she brought a bunch of her high school friends over. And so it was really just a bunch of high school kids having a party with one sad little kid sitting in the corner, pouting in the corner. So as you can imagine, like, I didn't really enjoy going to school. So one of the things I learned is that if I was sick, I didn't have to go to school. Something that I think we're all relearning in this era. But eventually my parents caught on to what I was doing. And so pretty much every day started with me saying, I don't feel well enough to go to school. And one of my parents putting their hand against my forehead saying, nope, you're fine, go to school. Regardless, right? But that was kind of the first real exposure I had to a measurement, right? This is a very, very simple temperature measurement. In some sense, I'm going to give you two definitions of what I mean by temperature. One, how warm or cold an object is. Can I use WRT with respect to? Okay. A given standard? So in that instance, the temperature measurement was not at all precise, right? What we're really checking is, was my forehead warmer or colder or the same temperature as my parents' hand? And quite frankly, I think on more than one occasion, it was just a cursory measurement of, regardless of what my forehead had felt like I was going to school. So that's our simple standard, and we're going to come back to to this kind of definition in a minute. A second definition that is going to take us a minute to get to is this idea that temperature is a measure of the average translational kinetic energy Can I use KE for kinetic energy? Average translational kinetic energy per particle in a given sample. So the temperature of the sample is a measure of its average translational kinetic energy per particle. Yay?
So when your dad or your mom were doing this, were they measuring the kinetic energy of your particles, your atoms, molecules?
To some extent, that's what temperature is. But what they were doing is barely passable as this first definition. On some level, we need these two definitions to agree.
Right.
But as a first pass, we're going to go with something like this is what that measure is. So temperature is also very much tethered to lots of material properties. And so it's not just perhaps the most common in our measurement in our arsenal. It's also a very important one. So you've probably noted thermal expansion. You've probably noted that a steel bar, when heated, expands in length, right? Pressure is, as we'll see shortly, tied to temperature. Electrical conductivity. If any of you have had like a property of engineering materials course, you might have run across this idea that electrical conductivity is also itself tethered to temperature, and it behaves differently depending on whether the thing is a conductor or, say, a semiconductor. So for a conductor, the conductivity tends to get worse as you raise the temperature in general. And for a semiconductor, the conductivity tends to improve as you raise the temperature. So
I heard there's like a heat conductor.
sure, and we are, by the end of the next chapter, going to talk about thermal conductivity or thermal conductance.
Okay.
So as a good rule of thumb, if it's a good thermal conductor, it's also a good electrical conductor. So it's a loose rule of thumb. So let's tackle this first definition first and come to the second. So you have to remember that because this is such a common measurement, that this is something that has been measured for a very, very, very long time. And so to that end, some of the early work in this predates the ability to easily ship stuff. And so I'll give you the following. Since we were just saying that a lot of material properties are temperature dependent, we're going to use water to describe a lot of this stuff. And so I'll tell you, water will freeze on our Celsius scale at 0 degrees, and it on the Fahrenheit scale it will freeze at 32 standard pressures. We could say that water boils at 10 standard pressures on the Celsius scale at 100 Celsius. Anyone know where it boils on the Fahrenheit scale?
212, I think.
212. There's 180 degrees Fahrenheit between the freezing and boiling. Yay? It also should be noted that temperature difference of 1 degree Fahrenheit is equal to a temperature difference of 5/9 of a degree Celsius. And so at this point you have 2 points and you have the slope, so you can come up with an equation converting from one to the other as you choose. Is water just magic? I mean, it's pretty convenient, right? That water freezes at 0 Celsius and boils at 100 Celsius standard pressures. Not really. The trick here is that you have to remember a lot of this groundwork was done, again, in this era before it was easy to ship stuff, right? So rather than sending you a thermometer, we'd send you the idea for a thermometer. And it's a lot easier to distribute the idea than it is to distribute the thing. Yeah? And so what we're going to argue for is that we should pick, however you're going to build your thermometer, we should pick something that can be calibrated so that your thermometer and my thermometer will agree. And so this calibration method needs to be ubiquitous. You guys know what I mean when I say ubiquitous?
No.
No.
I mean readily available, right? Something that's everywhere. And what I would argue is that water is a good choice for this, right? If someone doesn't have access to potable water, they have more pressing concerns than measuring the temperatures of things, right? And so pretty much anyone who has the spare time to be doing science has already figured out a source of water. Does that make sense?
Yeah.
And so should be able to calibrate their thermometer using the temperature dependence of water. We're okay with this.
Yeah. I just got a question.
Go for it.
Why do we consider absolute 0 degrees Kelvin?
We often will even just say 0 Kelvin, but that's coming shortly.
Okay.
So that is more tied to this statement, that temperature is a measure of the average translational kinetic energy per particle in a given sample. Yay enough for now. Okay, so now I believe that I can see this one, right? Okay. The other weird thing is that there is a substantial delay between when I do something and when it shows up on that screen.
That lag.
Makes me feel
Good stuff.
ghost-like. So, all right, so we had our ideal gas law. We made use of this in our last lab. By the way, when someone does watch this video, you guys will have to let me know whether the audio level is too low, too high, although it looks like I'm maxing out the microphone. So I'm going to guess too high. And if the writing on the screen is at all legible. Spencer?
When should we like expect to see this recording? Like Tuesday, Wednesday?
Yeah, give me probably a day.
Okay.
So I have to figure out some mechanism of putting up at least some form of captioning. So we have our PV equals nRT. We also have our PV equals nKBT. So in our last lab, we looked at Boyle's law. And what was Boyle's law? What was the special case involved of this for Boyle's law?
Constant temperature.
We fixed the temperature. And so in that case, and in all of these, I'm going to assume that we're not letting gas into or out of the system. And so in that case, the whole right side of either of these equations is held fixed. And so PV is a constant. We also had Charles's law. And I don't know whether or not that gets the extra S. I know we keep trying to teach me this, but so in this case, we're going to fix the pressure, and so we're going to say that V is equal to a constant times T. What I want to point out is that these two constants aren't the same, right? Gay-Lussac. I'm sure my French grandmother would yell at me for my pronunciation, but it's not like there's a video evidence of this.
There is.
It's recorded.
In that case, we're going to hold the volume fixed, and we have P is equal to yet a third constant times T. Is that maybe kind of sort of art? Sam?
What do you mean that the constants are not the same?
I mean that when I tell you that PV is equal to a constant here, and then when I tell you V is equal to a constant times T here, that this constant and this constant are the same value.
They're different.
They are.
For Gay-Lussac's law, that's for a fixed volume, right?
Yes, sir. Yeah, so assuming that we've held the number of moles or the number of molecules fixed in all of these, we're basically cycling through the other parameters that we can change, P, V, and T. Yay? So let's see if we can't sort this out. So I want to see if we can examine what Alexis was just asking about. So we have some gas bulb, and then oh goodness. to the best of my ability, which is clearly not excellent. A connection to some kind of reservoir.
At least you're not louder than the teacher down the hall.
Mad.
She's actually an awesome teacher. She was one of the teachers who trained me when I got here.
I don't know who that is. Who is it?
That is Ellen.
Ellen?
Ellen Coatney.
Never had her.
She is an awesome teacher. If you guys have a biology class to take, I recommend her.
Nope.
Retake on my biology.
So. I'd like to think that I'm goofier when I'm being recorded and that I can normally spell words, but I think the truth is that I'm just as bad at spelling and I'm just as awkward in my normal day-to-day life. There just isn't a camera roll. So when we spoke of our barometer last week, I was saying that there was as the fluid bell left a near vacuum here, again some residual gas pressure, but very 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 minimal, and so I want to make the same argument here. So let's see. I'll call that H. It is in fact. So here we can use this to determine the pressure of the gas in the bulb. Yeah. So in some sense, this is a closely related cousin to the barometer that we looked at last week. And so if let me just do this here and see if I can make it fit. If we plot pressure against temperature, so we put this gas bulb, say, in a pot of boiling water, and then we put it in a pan of ice water, and maybe we put it in a dewar full of liquid nitrogen, so that we specifically know these temperatures. Then we look at the pressure. We do this with different gases in the gas bulb. If we were doing this just with, I'm going to regret that. Yeah, I'm going to regret that. So maybe this one is boiling water, this one is our ice water then we can do this for a whole bunch of temperatures in between. And then let's say that we repeated those two measurements just with a different gas in the gas bulb. Maybe we see something like that. And then maybe for yet a third, we get something like that. That might not appear too interesting in its own right, but if we did this for colder temperatures, say liquid nitrogen, for say a third data point, maybe liquid helium, still colder. Or maybe if we just project these backwards.
That's
My inability to draw a straight line worked to our advantage here, because note that all of these seem to intersect back here. And so if you extrapolate backwards, you wind up having them all meet for a variety of ideal gases at a temperature you get to a zero pressure at minus 273.15 degrees Celsius, give or take. There's a couple of things that I want to see if we can note here. First, so a thermometer is going to be our device for measuring temperature. A thermometer measures its own temperature. So to that end, we're relying on something called thermal equilibrium. By this, what I mean is, if you place two objects in thermal contact, give them some means of transferring energy back and forth. If you place two objects in thermal contact, energy will transfer from the object at higher temperature to the object at lower temperature until they are at the same temperature. Does that make sense?
Yeah.
So when we're talking about a thermometer, does an ideal thermometer have a big resistance to changing its temperature or a little resistance?
A little.
Very, very little, right? So if you put a thermometer in thermal contact with something else, you want it to very readily move towards the temperature of the other thing, right? You want it to have very, very little resistance, as little as possible. You don't want to change the temperature of the thing that you're trying to measure, right? To that end, like with the thermometer you stick under your tongue, is that ideally suited to measure, say, the temperature of
Lava.
a big pan of water? Probably it's fine for that. But if I just took a single drop of water, is the thermometer a good tool for measuring that?
It's not sensitive enough.
No. Why wouldn't you want to use a household thermometer to measure the temperature of a single drop of water?
What's the size?
You're very likely to change the temperature of the water that you're trying to measure the temperature of, right? Does that make sense? So
It should be the same temperature, a pour of water or a drop of water.
even if they're the same temperature, right? So if the temperature of a big pan of water and a single drop of water is the same, if you took a thermometer and tried to use that thermometer to measure the temperature of either of them, well, there's probably significant enough thermal inertia of the giant pan of water that the thermometer is going to do most of the changing of temperature, right? But if you only have a single tiny drop of water, it's likely that both the thermometer and the drop of water are going to move and meet somewhere in the middle.
So the smaller the object is, the less resistance it has to changing temperature.
The less energy it will take to change the temperature, yes. So that's also on our list of to be seen soon. But I'm going to give you that Q is going to go as MC delta T, where Q is the energy absorbed as heat. So the energy required to be absorbed as heat to cause a change in temperature delta T is proportional to the product of MC and delta T, where M is the mass of the thing absorbing the energy as heat. C is this term that's used to describe how easy it is to change the temperature. It's kind of like thermal inertia. We call it specific heat. And delta T is how much you want to change the temperature. So far, so good. With our working definition that temperature is a measure of the average translational kinetic energy per particle in a given sample, I'd like to kind of expand on this a little, if I can, just for a second, and try and differentiate what I mean by average translational kinetic energy. First of all, you're okay with this idea of translational kinetic energy? That's the one that translational motion is the motion that carries me from point A to point B? That's all right? Okay. So let's play the world's most boring game show. I'll pitch it for you right now. You ever seen Let's Make a Deal? I'm old.
I think so.
So in kind of a pared down version of this, you're gonna get to choose between what's behind door number 1 and what's behind door number 2. And I'm gonna try and talk you out of it, regardless of whether you choose door number 1 or door number 2. And then we're gonna show you what's behind door number 1 and door number 2, and then everyone's gonna either cheer or laugh, right? But this is, you know, that's copyrighted already. So let me give you my version of the show. I'm going to tell you what's behind doors number 1 and 2, and then you can pick which one you want. I'm sure that this is suspenseful enough that everyone's going to tune in for this. Behind door number 1, there is one $100 bill. When I was a young person, that was a lot of money. Now you guys are like, what the heck? What the heck? Sorry. Behind